Imagine standing on the surface of the moon, a silent world frozen in time, unchanged for billions of years. How would you feel contemplating this unique lunar landscape, so different from anything you've seen on Earth? Take a moment to visualize this panorama. The dusty, chalky ground beneath your feet, dotted with rocks and craters as far as the eye can see. A horizon that seems to melt into the inky black of the sky, punctuated by the distant twinkling of stars. How would you feel, lost in this immensity, faced with a spectacle both magnificent and desolate? Dear traveler, welcome. Today we're off on an incredible exploration of the moon. But before you set off on this new adventure, remember to like the video and subscribe to the channel so you don't miss a thing. Thank you and have a great trip. The moon, Earth's only natural satellite, is the closest and brightest celestial object after the sun. Throughout history, the moon's mysterious beauty has been a source of fascination and curiosity, inspiring a rich cultural and symbolic tradition. The moon's surface is a canvas marked by ancient stories, inscribed in rock and dust, offering an awe-inspiring vision of the hostility of outer space. Absent the usual terrestrial erosion processes such as wind or water, it preserves its past from distant times. The lunar surface is inert, devoid of life or movement. What characterizes it above all is the absence of atmosphere, with abrupt transitions from day to night at the first ray of sunlight. The moon is absolutely quiet in the absence of an environment capable of carrying sound. The moon rotates on an axis inclined only 1.5 degrees to the ecliptic, eliminating the seasons and their changes. At the lunar poles, sunlight strikes almost horizontally, creating perpetual darkness and extreme cold. Although the lunar surface is altered by factors such as meteorite impacts and high-energy radiation, these changes are slow and subtle, but profound over astronomical time periods, affecting the regolith, the moon's surface layer. When a meteorite strikes the moon's surface, it causes a small explosion, hurling particles of soil and meteoric material in all directions. Most of these particles then escape the moon's gravity. The lunar geography is essentially divided into two types of regions: the Maria, or lunar seas, which are vast plains of dark basalt, occupying 17% of the surface, and the clear, intensely cratered highlands, which make up the remaining 83% of the lunar surface. The high plateaus or continents are characterized by their pronounced relief and an abundance of craters of varying sizes and preservation. Lunar seas, on the other hand, are characterized by their relatively flat topography and fewer craters. Seas lie below the level of the continental surface. For example, the Sea of Rain is located at a depth of 3 kilometers or 2 miles. while the Sea of Vapors lies 2 kilometers or 2 miles below the average level of the lunar surface. Obviously, these seas contain no water, but they were named seas because of their dark hue. Smaller, darker areas were referred to by analogy with seas as bays, lakes, and swamps. The distribution of marine areas on the lunar surface is extremely uneven. The main seas are concentrated in the Moon's visible hemisphere. In the northern hemisphere, seas occupy twice as much of the lunar surface as in the southern hemisphere. These seas are mainly made up of basaltic lava, with lower, more extensive reliefs appearing as folded veins, generally indicating places where more recent lava flows are overlying those already present. Near these folded veins, the thickness of the lava flows may be minimal. The names of the lunar seas are not random. In the eastern part of the visible hemisphere, we find the Sea of Fertility, the Sea of Tranquility, the Sea of Serenity, and the Sea of Nectar, while in the western part, we find the Ocean of Storms, the Sea of Rains, and the Sea of Vapors. These names are explained by the widespread belief in the mid-17th century that the phases of the Moon influence weather conditions on Earth. The Ocean of Storms is the largest marine formation, bordered to the northeast by the Sea of Rain, and to the south by the Sea of Clouds and the Sea of Vapors. On the eastern half of the disk visible from Earth, the Sea of Serenity, the Sea of Tranquility, and the Sea of Fertility stretch in a row from northwest to southeast. These expanses are bordered to the south by the Sea of Nectar and to the northeast by the Sea of Chryses. Relatively small seas occupy the border between the visible and inverted hemispheres, such as the Mer Orientale, the Mer Marginal, and the Mer de Smith, and the Mer Austral. On the hidden side, only one notable marine formation exists, called the Sea of Moscow. In addition to the seas, there are also ring-shaped mountains scattered over vast areas, taking on a round shape in the central parts of the visible lunar disk, and an elliptical shape in the marginal parts. These circular mountains take the form of large and small round formations, with varying depths, surrounded by ramparts rising 1.5 kilometers, or 1 mile, above the surrounding terrain. Ring mountains with a diameter greater than 35 kilometers or 22 miles are called lunar cirques, while smaller ones are called lunar craters. Smaller craters are scattered all over the Moon's surface, whether on its plains, at the bottom of seas, on mountain ranges, or other formations. Around the middle of the 17th century, Polish astronomer Jan Hevelius suggested that lunar mountains be given the same names as those on Earth. The Sea of Rain retains only one of its outer rings, in the form of the mountain ranges called the Alps, the Caucasus, the Apennines, and the Carpathians. The Nectar Sea is surrounded by the Altai and the Pyrenean Mountains. The Eastern Sea is surrounded by the Cordillera Mountains. The Apennine Mountains appear to be the highest on the Moon, with individual ridges reaching up to 5.6 kilometers, or 3.5 miles, above the surface of the nearby Sea of Rain. The Jura Mountains rise to around 4 kilometers or 2.5 miles above the Bay of Rainbows, while in the Carpathians, only a few hills reach an altitude of 2,300 meters or 7,500 feet above the surrounding area. The most striking features of the lunar surface are its craters. A crater with a clear, well-preserved bottom indicates relative youth, while those with degraded bottoms are generally older. Large craters often feature a central mountain and terraces along their inner walls, as in the case of the Copernicus and Aristarchus craters. In older craters, such features as mountains and terraces are less common. Some craters have ray systems, bands of light extending radially from their rim. These rays are not always visible, appearing mainly during the full moon. They are less visible during other phases and often absent near the terminator, the fictitious line that separates the illuminated and non-illuminated sides of the moon. Craters with ray systems are found in craters of various sizes, from the Tycho crater, with a diameter of around 85 kilometers or 53 miles, to smaller but equally young craters. Networks of various fissures and rays emanating from crater bases, as well as furrows and light rays, are frequently observed. The Moon has several dozen such craters with ray systems that are visible on the side of the Moon that is accessible to us at full moon. Valleys, distinct and isolated depressions several kilometers wide and tens or hundreds of kilometers long, are found on the slopes of vast mountainous regions, such as the Alpine Valley, as well as in continental areas, such as the Rita Valley. Narrower, longer, but less steep troughs, which maintain a uniform width along their entire length, are called furrows, such as the Cersalis furrows, which often extend for hundreds of kilometers, irrespective of the surface topography. Steep faults are referred to as fractures. In the lunar seas, we sometimes find cornices, typical faults, such as the edge of the Strait Wall in the Sea of Vapors. The far side of the Moon draws particular attention to the very large annular structures called basins, which often exceed 300 kilometers or 186 miles in diameter. Among the largest are the South Pole Aitken Basin, the Oriental Sea, the Hertzsprung crater, and the Sea of Moscow. In addition to their outer ring, these basins often have an inner ring, whose diameter is generally half that of the outer ring. Occasionally, however, the inner rings are severely damaged. Some of the large basins on the far side of the Moon are exactly opposite the seas visible on its illuminated side. For example, the Korolev crater is the opposite of the Sea of Fertility, while the Hertzsprung crater corresponds to the Sea of Tranquility. To the northeast of the Oriental Sea, immense chains of craters extend radially for distances of up to 1,000 kilometers. These chains include craters with an average diameter of 20 kilometers or 12 miles. The craters, individual mountain peaks and ridges are named after eminent astronomers and scientists in various fields. The exception is 12 craters named after living cosmonauts and astronauts. Let's take a closer look at the Moon. Let's begin our journey with topographical details of the Moon's visible face, i.e., the side of the Moon facing the Earth. The Sea of Tranquility is in fact a lunar pond, although these lunar expanses are devoid of water. These formations were named seas by ancient astronomers, who misinterpreted them as bodies of water. In fact, when we observe the Moon, particularly the side visible from Earth, we can distinguish regions that are darker than the rest. These dark areas, when compared to a grayscale Earth model, could easily be mistaken for seas. Although recent discoveries have revealed water beneath the lunar surface, this underground water does not constitute seas in the conventional sense. The Sea of Tranquility is formed of basalt. Seen from Earth, it appears darker than the surrounding lighter, higher-lying areas, which reflect more sunlight. When colors are extracted from various photographs, the Sea of Tranquility reveals a slightly bluish hue, probably due to the higher concentration of metals in the region. Through sample analysis, scientists have discovered that the area contains basalts, a type of volcanic rock found on both the Moon and Earth. This data has fueled a number of theories about the Moon's genesis, including that of a giant impact, which is widely accepted today. Astronomers speculate that the intense bombardment of the lunar surface by meteorites led to the ejection of the still hot inner mantle, forming special magma basins in the impact cavities. The Moon subsequently cooled, solidifying the magma and forming the lunar seas. This vast lunar zone, with a diameter of around 873 kilometers, or 540 miles, is far from simple. It reflects the turbulent periods of the lunar past, sculpted by ancestral volcanic activity billions of years ago. At the heart of the Sea of Tranquility's geological history are the impressive basaltic lava flows, evidence of ancient volcanic eruptions that have profoundly marked the lunar landscape. It is these massive effusions that have formed this characteristic smooth plain. The edge of the Sea of Tranquility has a highly irregular relief, with only a clearly delineated fraction comprising cliffs. It is difficult to compare it to a simple geometric shape. In the vicinity of this formation, the terrain is flat, with elevations almost nil. In the northern part of the Sea of Tranquility, where the telescope's resolution capabilities reach their limits, it is possible to observe certain types of marine domes, often generated by the effusion of volcanic basalts. The origin of these formations is attributed to endogenous processes, mainly volcanic, and their flattened appearance suggests that they were shaped by the flow of viscous lava. Small craters dot the surface, testifying to the countless impacts suffered by the Moon throughout its history. These craters of all sizes illustrate the cosmic collisions that have shaped the Moon over billions of years. In addition to craters, the Sea of Tranquility also boasts unique features such as grooves. These narrow formations, shaped by ancient lava flows, trace paths across the landscape, revealing clues to the moon's volcanic past. They are the remnants of once fiery rivers of lava, bearing witness to their devastating force. And as if craters and grooves weren't enough to pick our interest, this lunar region also features ridged crests, formations that appear to be ripples on the moon's surface. They probably formed when the lunar crust contracted, offering a glimpse into the geological processes at work. These ridges provide key data on the moon's geological evolution, revealing the dynamics that have shaped its surface through the ages. Unlike the Sea of Tranquility, its younger neighbor to the north, the Sea of Serenity, has a well-defined coastline with numerous cliffs. Much of its seabed is lighter in hue than that of the Mer de la Tranquillité. In the strait separating the Serenity and Tranquility seas, we find the Plinius crater, measuring 41 kilometers or 25 miles in diameter, and the Dawes crater, with a diameter of 18 kilometers or 11 miles. To the right, on the side of the Sea of Tranquility, north of the Sea of Serenity, part of the continental surface is trapped. On the edge of this continental zone, along the Sea of Tranquility, lies the clear, well-preserved Vitruvius crater, measuring 29 kilometers or 18 miles in diameter, whose floor is filled with lava. Chances are you've observed the moon through a telescope, spyglass, or binoculars, and noticed a very distinctive crater in the southern hemisphere of the moon's visible face. Tycho is the crater that catches everyone's eye during the full moon. Its luminosity, combined with its dark ramparts and the long rays of light emanating from it, give it a distinctive appearance. No other ray crater has such a remarkable dark circular structure. This dark circle, clearly visible in telescopes and photographs, represents the distribution of a virtually continuous substrate of dark, glassy, molten material generated by the impact. This structure is remarkably well preserved, as the crater is still so young that this deposit has not been altered or mixed with other rocks by the myriad small impacts. This regular but slow process, known as space weathering or spatial erosion, also contributes over about 1 billion years to erasing the bright rays around the craters. This crater is known as Tycho, after the 16th century Danish astronomer Tycho Brahe. Of course, there are many much larger craters on the moon. However, Tycho is undoubtedly the most remarkable of them all. It is located in the moon's southern hemisphere, where the Ocean of Storms and the South Pole, Aitken Basin, meet. On full moon nights, the large Tycho crater stands out as one of the most remarkable lunar features. It is surrounded by a ring of dark matter, extending beyond its ramparts for about a crater radius. During the moon's transition from first quarter to full moon, Tycho's appearance changes dramatically, from a large gaping crater to the epicenter of a fantastic ray system. The crater is relatively young, as evidenced by its rays crossing various lunar terrains. Scientists estimate that the Tycho crater was formed some 107 to 110 million years ago, following the impact of a large asteroid on the lunar surface. This makes Tycho one of the youngest craters on the Moon's visible surface. During a space mission, a space probe was able to capture a series of detailed photographs highlighting the splendor of the Tycho crater. The images, taken from a distance of 30 kilometers or 30 miles from the crater's surface, reveal that at the center is a huge boulder measuring around 120 meters or 400 feet, although exactly how it got there remains a mystery. Smaller cobblestones detached from the rock can be seen on the slopes. The crater has a diameter of around 85 kilometers or 53 miles. Its central summit rises on average 2.4 kilometers or 1.5 miles above the crater floor, while the outer rim of the crater reaches a height of 4.8 kilometers or 3 miles. Its inner slope has a well-defined terraced structure. The area surrounding the crater is dotted with numerous other impact formations of varying sizes, some resulting from the larger debris ejected during the Tycho formation. The crater is surrounded by a vast system of light rays, measuring up to 1,500 kilometers or 930 miles in length. Although visible at all times, these rays are particularly sharp on full moon nights. Observing Tycho around the full moon with binoculars or a small telescope reveals that the light rays are not evenly distributed in all directions. These light rays extend far to the east, south, and northwest, but none to the west. The nature of these rays has long been the subject of debate. Early theories suggest they might be salt deposits from evaporating water. Later, many researchers considered that they could be deposits of volcanic ash. Once the idea that the Tycho crater had been formed by an impact was widely accepted in the 1960s, many researchers began to favor the following hypothesis. The rays were the result of the deformation of lunar rocks following this impact. The impact threw more soil and rock downwards, widening and extending the rays. Freshly excavated lunar material shines, but its brilliance diminishes over time. The rays from the Tycho lunar crater remain bright, as they have not yet been affected by the solar storms, cosmic rays, and micrometeorites that darken them and degrade them to dust. The large luminous halo surrounding Tycho is twice as wide to the east as to the west, typical of a crater formed by an oblique impact. Thus, the impactor that formed the Tycho crater, an asteroid probably 10 kilometers or 6 miles in diameter, approached at a shallow angle to the west to form an off-center ballistic pattern. Between 3 and 4 days after impact, a fraction of the debris thrown up by the collision must have reached the Earth, triggering a particularly spectacular meteor shower. At that time, just over 100 million years ago, the dinosaurs and other reptiles that populated the Earth probably witnessed this titanic collision. Like other lunar seas, the ocean of storms is a flat expanse of basalt, formed by the hardening of magma. In fact, this region does not differ structurally from other lunar seas. Its classification as an ocean rather than a sea is due solely to its exceptional size. Dominating the northwestern part of the lunar surface, the ocean of storms extends over a distance of more than 2,500 kilometers, or 1,500 miles. Its origin dates back some 3.5 billion years, and since then, subsequent impacts, some of them large-scale, have altered its outer contours. In the past, its appearance on the face of the moon during the second quarter was associated with bad weather, hence its name. Most of the other seas are roughly circular in shape, suggesting that they may be the result of bombardment of the lunar surface early in the moon's history. Because of its immense size and presumed rounded shape, it is generally assumed that the appearance of the ocean of storms is due to a major impact having struck the moon and perforated its crust. Magma subsequently erupted, forming immense plains that eventually gave rise to the ocean of storms as we know it today. It's possible that this ocean was formed in the same way, but if so, the impact that created it would have had to be truly enormous. Various other theories have been put forward as to the formation of the ocean, offering alternatives to the impact hypothesis. According to these researchers, it is possible that this area merged as a result of deep mixing within the moon, leading to a significant accumulation of heat-generating radioactive elements in the crust and mantle of this lunar part. It is perhaps more likely that this vast area was subjected to the internal forces of the moon's initial structure, causing magma to flow freely over vast areas of its western hemisphere before solidifying to create the flat surface of the plain. Eventually, the pressure exerted by the weight of lava on the surface would have compressed the crust, closing the faults and putting an end to the flooding. Subsequently, the lava plains would have cooled, while subsequent impacts would have given rise to the other superimposed basins. The scale of the situation is astonishing. Imagine a lava eruption so large and so long that it flooded 2.5 million square kilometers of the lunar surface. That's an area equivalent to a quarter of the surface of Europe. Despite its apocalyptic aspect, this new idea has many positive points. First of all, observations seem to agree perfectly with this hypothesis. But scientists still have reservations about the idea of a single impact, since the consequences of such an event would have been so far-reaching that they would have had to leave many traces. For example, the shock wave would have penetrated the lunar crust and propagated around the moon, converging at the opposite point. This would have released a significant amount of energy there, resulting in chaotic, distorted terrain in the area. However, no such features have been identified in these regions. Despite its vast extent, the inner surface of the ocean of storms is generally uniform, with the exception of a few small scattered craters. The most notable of these is Kepler, a radiated crater about 31 kilometers or 20 miles in diameter, bordering the ocean of storms. At the ocean's margins, there are several more remarkable surface features. On a plateau near its northern shore is another crater named Aristarchus, comparable in size to Kepler and one of the moon's brightest spots. To the east of the Aristarchus crater, the ocean of storms meets the vast Sea of Rains, and part of their common border is marked by a chain of mountains. South of these mountains lies the vast terraced crater known as Copernicus, stretching nearly 93 kilometers or 57 miles from rim to rim. South of the Copernicus crater, delimiting the southeastern limits of the Ocean of Storms, lies a mountain ridge that was once considered an integral part of the ocean itself. However, in 1964, this region became the first part of the Moon to be seen in detail by a terrestrial probe from Earth. The Montes Apenninus may not be the highest lunar mountains, but they are undoubtedly the most impressive and spectacular. Named after the Apennine Mountains in Italy, they form the southeastern boundary of the Sea of Rains, the largest and most significant of the regular lunar seas, and dominate much of the landscape during each lunar phase. The Apennines do not form a continuous boundary around the Sea of Rains, but it is likely that this was once the case. The formation of the Apennine mountain range dates back some 3.8 to 3.9 billion years to the impact of an asteroid-sized body, which hollowed out the Rainy Sea Basin. This impact lifted the nearby crust, forming the arched mountain range known as the Montes Apenninus. On Earth, mountain ranges take millions of years to form, but the magnificent landforms surrounding the Rainy Sea were created in a matter of moments. The event that led to the formation of the Mare des Pluies Basin occurred several hundred million years before the basalt eruptions that filled the basin. Near Eratosthenes, one of the most remarkable and best-preserved craters, the Apennines follow the edge of the Sea of Rains, separating it from the smaller, darker Sea of Vapors. This mountain range boasts over 3,000 peaks stretching for 600 kilometers, or 370 miles. The view is particularly striking at first lunar quarter, when the peaks cast their long, sharp shadows over the plain. The highest point in the Apennines, Mons Huygens, reaches an altitude of around 5,500 meters, or 18,000 feet from its base to its summit, above the lunar surface, more than half the height of Mount Everest. The mountain is named after Christian Huygens, the Dutch astronomer who discovered Titan, Saturn's largest moon. At the eastern end of the mountain range lies Mons Hadley. To the north, the Sea of Rains is framed by the Alpine Mountains, which do not join up with the Apennines. There is a gap between these two formations, allowing the soil of the Mare des Pluies to join that of the adjacent Mare de la Serenité, a difference in altitude and age then becoming apparent. Although the lunar Montes Alpes don't rival the Apennines in terms of importance, this relief is of particular interest thanks to unique features found nowhere else on the Moon. In particular, the Alpine Valley, a gigantic crevasse running through the mountains, deserves special mention. The Alpine Valley stands out visually as one of the most impressive formations on the lunar surface. The Alpine Valley crosses the Montes Alpes over 190 kilometers or 120 miles in length, and 20 kilometers or 12 miles in width. This valley was formed by the collapse of the lunar crust between parallel faults. It is likely that this valley was created simultaneously with the impact that formed the Sea of Rains. The surface of the valley is covered with dark lava rocks, and at sunrise, the steep slopes reaching up to 1,000 meters, or 3,300 feet, at the western end, are magnificently illuminated. Further out, just a few kilometers from the Sea of Rains, the valley opens onto a large oval area known as the Great Amphitheater. With a quality telescope, it's possible to see the 550-meter or 1,650 feet wide fissure that runs along the bottom of the Alpine Valley. This fissure, located in the center of the valley, is probably an ancient lava conduit whose roof has collapsed. Beneath the Montes Alps, to the southeast of the Moon, lie the Montes Caucasus, another mountain range that plunges beneath a lava-covered plain, linking the Sea of Rain to the Sea of Serenity to the southeast. Finally, there's the Sinus Iridum, also known as the Bay of Rainbows. It appears to have once been a major crater on the edge of the lunar sea, but lava flows have risen to submerge the coastal wall, leaving it barely discernible and creating a vast bay. This spectacle is particularly striking when the sun rises over the bay. The sun's first rays first illuminate the peaks on the other side, leaving the bay plunged into darkness. This phenomenon is often referred to as the jeweled handle and occurs once every lunar phase, providing a remarkable example of the chiaroscuro effect. The Montes Apenninus are part of a distinct geological feature observable on the Moon, known as multi-ring impact basins. Landing in such regions is essential to deepen our understanding of the formation and evolution of multi-ring impact basins, not only on the Moon, but also on other planetary bodies. During full moon phases, the vast dark lunar plains are easily visible to the naked eye on the Moon's visible side. We now understand that they are actually huge basins of frozen basaltic lava from ancient times. Lunar scientists believe that the Sea of Rains, considered the second youngest lunar basin, formed around 3.85 billion years ago when a protoplanet collided with the Moon. The Sea of Rains is an immense basin composed mainly of basalt, measuring over 1,000 kilometers or 620 miles in diameter. Until now, the precise size of the object that formed such a basin was unknown. Recent calculations revealed that the diameter of the colliding asteroid was much larger than previously estimated, reaching around 250 kilometers or 155 miles, whereas it had previously been estimated at 80 kilometers or 50 miles. According to planetary scientists, this estimate is conservative. The actual diameter of the asteroid could exceed 300 kilometers or 190 miles. Scientists point out that the asteroid's imposing size justifies its classification as a protoplanet. This collision marks an important period in lunar history, known as the Late Great Bombardment, sometimes referred to as the Lunar Cataclysm. The collision took place between 4.1 and 3.8 billion years ago, a time when the Earth-Moon system and other inner planets experienced a significant increase in the number of impacts by celestial bodies. Although the exact origin of this increase in bombardments remains uncertain, some planetology specialists suggest that it could be the result of orbital modifications of the solar system's giant planets, induced by interactions with volatile materials such as gas, dust, or even small space debris. It is possible that these disturbances affected the asteroid belt between Mars and Jupiter, as well as the comets of the Kuiper belt at the outer edge of the solar system, causing eccentric orbits that brought them into contact with the inner planets, Mars, Earth, Venus, Mercury, as well as the Moon. After the formation of the rainy sea basin following the initial impact, further collisions with space rocks created smaller, more recent craters inside. Subsequently, over hundreds of millions of years, volcanic eruptions covered the region with lava, forming lava-filled craters known as lunar seas, leading to the formation of a relatively flat surface over a considerable area. The rainy sea region, with its mountains, ridges, canals, plains, and craters, is a fascinating testimony to the Moon's geological past. The Sea of Rains has an average depth of around 5 kilometers or 3 miles. It is surrounded by 3 concentric mountain ranges, rising to around 7 kilometers above the surrounding surface. The outer mountain range, which extends over a diameter of 1,300 kilometers or 800 miles, comprises 3 distinct mountain ranges: the Carpathians to the southwest, the Apennines to the southeast, and the Caucasus to the east. The mountain ranges are less pronounced in the north and west. Unlike terrestrial mountain ranges, these are not the result of tectonic uplift, but were formed by the impact that hollowed out the rainy sea. It's a bit like a billiard ball falling into a vat of thick, viscous mud, leaving a well-defined circle of ridges around the point of impact. Then, the Mer des Pluies basin filled with lava. This transformed the sea basins into what were, for a time, truly liquid seas. For several hundred kilometers around the Mer des Pluies, there are marks of rock emission in the form of furrows and trenches. This relief appeared following a collision with an asteroid, when fragments ejected from the impact bombarded the lunar surface at low angles. According to experts, the collision that formed the Sea of Rains had an impact on the entire lunar crust due to seismic waves passing through the young moon. As you explore the Sea of Rains, you'll have spotted a remarkable feature at its northwestern end, known as the Bay of Rainbows, a gigantic crater whose diameter measures around 236 kilometers, or 150 miles across. Surrounding the Bay of Rainbows from northeast to southwest is a low mountain range known as the Jura Mountains. On the south side, the entrance to the bay is marked by 2 distinct promontories, the western Heraclides promontory and the eastern Laplace promontory. When the famous Italian astronomer Giovanni Riccioli observed this lunar zone in 1651, he was struck by its resemblance to a terrestrial bay. It's important to remember that at the time, astronomers believed that the Moon, like the Earth, had continents, seas, and features such as lakes and swamps. In naming this plain the Bay of Rainbows, Riccioli had no idea of its true nature, which is hardly surprising given that this bay is distinguished from lunar craters by the absence of a central hill and the southern part of its rim. The astonishing origin of the Bay of Rainbows has given rise to many theories. In one investigation, scientists proposed that a gigantic cosmic body had collided with the lunar surface in the northwestern region, forming the bay before continuing on its course to create the Sea of Rains basin and its inner ring of mountain ranges. However, more recent research has revealed that the Bay of Rainbows and the Archimedes and Plato craters are slightly more recent than the Sea of Rains basin, leading to the dismissal of this hypothesis. Today, the most credible theory concerning the origin of the Bay of Rainbows is that following the formation of the Sea of Rain basin, a cosmic rock impact occurred on the lunar surface. This collision took place near the edge of the basin, where the topography sloped slightly towards its center. Subsequently, the formation of the Sea of Rains began, with lava flows progressively filling the basin and overflowing onto the northern edge of the Bay of Rainbows. Nevertheless, this explanation encounters a major difficulty. If the southern rim of the Bay of Rainbows was indeed covered by a lava flow, then we should see a gradual decrease in its height over time. On the contrary, the crater rim seems to maintain an almost constant height along its entire length, from west to east. Another fascinating hypothesis has been put forward, according to which, following a subsidence of the basin floor, a fault formed, passing beneath the southern rim of the crater. This rim would then have fractured and collapsed, with its debris submerged by the lava, just like the fault itself. To prove their theory, the researchers point to the concentric grooves preserved in the Archimedes crater region, Rima Bradley and Rima Hadley. Such grooves have been identified in most lunar basins, and according to the scientists, suggest deformation and subsidence of the basin floor. The most eye-catching observation at Rainbow Bay is undoubtedly the Lady's Head, a particularly remarkable lunar feature. The profile of a woman first appeared on a map of the moon made by the famous astronomer Jean-Dominique Cassini in 1679. It is presumed that Cassini depicted a real woman, perhaps even his own wife, on his map. However, there are other versions, such as a reference to the former Queen of Sweden, Christine, a friend of Cassini's with a passion for science, or a French queen. The Copernicus crater is one of the moon's most significant features. Although considered to be of average age by lunar standards, estimated at 800 million years, the crater is surprisingly well preserved and remains surrounded by a remarkably visible system of rays. This characteristic makes it easy to observe, even with a small telescope or binoculars. The images captured by the space probes reveal a section of the crater's central summit. This is divided into 3 distinct zones, rising 1,300 meters, or 4,300 feet, above the Copernicus floor. The mountains at the summit feature several strata composed of material ejected during the impact. Named after the Polish astronomer Nicholas Copernicus, the crater has a diameter of 93 kilometers, or 60 miles, and is located in the eastern part of the Ocean of Storms. Its impact shaft is not circular, but rather polygonal, rising more than 3,800 meters, or 12,500 feet, above the surrounding surface. Unlike most lunar craters, the floor of the Copernic crater has never been covered by lava. This is explained by the fact that it was formed after the end of the period of volcanic activity. This lunar ring emerged following the impact of a 7-kilometer asteroid. Such a collision with the Earth would have devastating consequences for the modern world. The colossal energy stored in the falling celestial body would instantly convert into an explosion of gigantic proportions, and the point of impact would experience temperatures far higher than those of the sun's surface. At the heart of the Copernicus crater are isolated, interconnected hills stretching 1.2 kilometers, or 1 mile above the surrounding area. These central peaks typically begin to appear in lunar craters larger than 15 kilometers, or 9 miles in diameter, resulting from changes in the forces at play during the initial impact. Rocks at the point of impact adopt a plastic behavior and straighten immediately after the formation of the impact cavity. This effect is similar to that observed when a drop falls onto a surface. According to scientists, the material making up the central peaks of Copernicus comes from a depth of 30 kilometers, or 18 miles. One of the distinctive features of the Copernicus lunar crater is a radiating network of secondary craters, reminiscent of an area hit by aerial bombardment. In this case, however, the bombardment was triggered by huge boulders ejected from the main crater at a speed of around 1,500 kilometers per hour, or 930 miles per hour. And because the ejected material was moving at a slower speed than the impactor, the explosion usually associated with such impacts did not occur. This is why Copernicus's secondary craters are elongated rather than circular. On the Moon's surface, a dark layer of material slowly forms, subject to the action of micrometeoroids and cosmic radiation. When this layer is covered by lighter material ejected from the point of impact, light rays form around the craters. This is also the main reason why we only observe these features in more recent formations on the Moon. In general, craters with visible rays are only a few 100 million years old. Copernicus, for example, is one of the oldest craters with well-defined rays. Recently, a group of researchers published a paper attempting to find the cause of the most recent lunar impacts. Analysis of 59 craters revealed that 7 of them formed simultaneously with Copernicus. So, around 1 billion years ago, the Moon was subjected to increased cosmic bombardment. The authors of the study even identified a prime suspect around 900 to 1,500 million years ago. A collision occurred in the asteroid belt between Mars and Jupiter, giving rise to a family of asteroids known as the Eulalia. The theory goes that the material from this collision triggered a storm of rocks that culminated on the Moon around 1 billion years ago. And it wasn't just the Moon. The Earth was not spared the bombardment at that time. It is estimated that both bodies received a deposit of material weighing around 30 to 60 times the weight of the impactor that caused the mass extinction 66 million years ago. So, Copernicus probably had counterparts on Earth, but traces of their existence have long since disappeared from our active planet. While the Moon's visible side continues to fascinate and amaze, its dark side remains shrouded in mystery. Seductive and out of our direct view, the Moon's dark side has long captivated the imagination. In the 20th century, as the first probes were sent into space, scientists began to wonder what might be hidden behind this little-known part of our satellite. Contrary to popular belief, the term dark side of the Moon does not mean permanent darkness. In fact, it refers to a hemisphere that remains invisible from Earth due to a synchronous rotation, where the Moon's rotation period corresponds to that of its orbital revolution. This remarkable phenomenon means that only one side of the Moon is perpetually hidden from our planet. As a result, the far side of the Moon is not constantly plunged into darkness. Although only one side of the Moon is visible from Earth, this does not mean that we only observe 50% of its surface. The Moon, like many celestial objects, follows an elliptical orbit with a certain eccentricity, which measures how far its orbit deviates from a perfect circle. Because of the Moon's distance from Earth and the slight inclination of its orbit, we can observe the Moon's north and south poles from Earth. The first glimpse of this unexplored region was offered in 1959 by the Soviet space probe Luna 3, which captured the first photographs of this little-known face. Subsequent missions, such as Chang'e, have provided a wealth of valuable data and images, shedding light on the previously hidden landscape. The Moon's far side offers a very different landscape to its visible side. One of the most striking distinctions between the hidden side and the more familiar side of the Moon is the absence of vast plains of dark basalt, known as the seas. The hidden side boasts just two large seas, known as the Sea of Dreams and the Sea of Moscow, in contrast to the visible side, which features a multitude of lunar seas. Instead, the dark side is mainly characterized by rugged high plateaus, dotted with craters and mountain ranges. Of the largest lunar craters in terms of diameter, the top 9 are found exclusively on the far side of the Moon. The South Pole Aitken Basin stands out as the largest crater on the far side of the Moon, attracting the attention of researchers and observers alike. What's more, this lunar region is characterized by a thick layer of crust, as well as an abundance of craters, bearing witness to its cosmic impact history. This striking contrast has led scientists to suggest that the geological processes that have shaped this face of the Moon offer a glimpse into its turbulent past. Another distinctive feature of the Moon's far side is its absolute silence. Isolated from terrestrial radio waves, this face offers astronomers and scientists a rare opportunity to observe the universe without the interference of terrestrial signals. This opens up a new era in the exploration of the universe and paves the way for future scientific advances. But why should the visible side of the Moon show more volcanic activity and lava flows than the hidden side? One widely accepted theory suggests that early in the history of our solar system, a dwarf planet in formation collided with the Moon. The impact would have thrown up huge quantities of material, which would then have been deposited on the Moon's surface, burying the far side under 5 to 10 kilometers of debris. This debris would make up a large part of the lunar crust and could still be detected today. Another theory is that the far side of the Moon has a thicker crust. During the formation of the Earth and Moon, heat from the still molten Earth would have delayed the cooling of the Moon's visible surface. On the other hand, the hidden side could have solidified more rapidly, forming a thicker crust. This would have led to meteoroid impacts on the visible side, which in some cases would have pierced the thinner surface down to the still molten mantle, releasing lava to the surface to create the lunar seas. On the other hand, if a meteoroid were to strike the far side of the Moon, the thicker crust would not be perforated, resulting in the formation of valleys, craters, and high plateaus, but not lunar seas. This formation is located on the southern far side of our Moon, and owes its name to two objects located at opposite ends: the Moon's south pole and the Aitken crater. The South Pole Aitken Basin stands out as the largest lunar crater, occupying a remarkable place on the far side of our natural satellite. With an impressive diameter of around 2,500 kilometers, or 1,550 miles, it ranks among the largest craters in the solar system. Its depth is equally remarkable, plunging 8 kilometers or 5 miles below the lunar surface, making it a unique object of study for exploring lunar strata. In addition to its size, the South Pole Aitken Basin is also one of the oldest lunar craters, dating back to the earliest stages of lunar history, some 4.2 to 4.3 billion years ago, a period in the history of the solar system known as the pre-Nectarian epoch. As a result, this particular formation is a rare vestige of the time when the process of planetary body differentiation was underway, marking the separation into core, mantle, and crust. Its age makes an essential element for understanding the evolution of the lunar and solar systems. Exploration of the South Pole Aitken Basin is far more than just an academic curiosity. It represents a treasure trove of geological knowledge, providing insight into the Moon's structural integrity and the possibility of finding precious resources such as water, ice, and rare minerals. This study plays a vital role in the planning of future lunar missions, whether manned or unmanned. By exploring this vast lunar crater, scientists have the opportunity to refine their theories on the formation of the Moon and the evolution of the early solar system. Its origin is attributed to a massive impact event that not only created the basin itself, but also significantly influenced lunar geology. In-depth study of this vast crater continues to provide vital information on the Moon's composition and internal structure, as well as on the geological processes that have shaped the lunar surface over billions of years. Until the 1990s, little was known about the basin. A multispectral survey conducted by NASA's Clementine spacecraft in 1994 revealed that the surface of the depression contained more iron oxide and titanium dioxide than the lunar peaks, making it darker. Some researchers support the hypothesis that the crater resulted from a collision between the young Moon and a massive cosmic body. Such an event would have shaken the entire Moon, as the size of the depression left after impact exceeds the lunar radius. Vertical impact models suggest that the asteroid would have stripped significant amounts of mantle material to depths of 200 kilometers, or 125 miles. However, observations show that the crater floor is mainly covered with rocks from the lunar crust. Another group of scientists argue that this suggests that the basin was not formed by a typical high-speed vertical impact, but could have resulted from a low-speed body crashing at an acute angle, but reaching great depths on impact. The force of the impact that formed the basin was so considerable that it most likely had an effect on the entire Moon, offering an exceptional opportunity for study in planetary geology and impact dynamics. Indeed, simulations of near-vertical impact suggest that the resulting fireball may have carried large quantities of material from the mantle to depths of up to 200 kilometers or 125 miles below the surface. However, observations to date do not confirm the mantle composition for this basin, and crustal thickness maps suggest the presence of around 10 kilometers or 6 miles of crustal material beneath the basin floor. For some researchers, this suggests that the depression was not formed by a typical high-speed impact, but could rather have resulted from the collision with a low-speed projectile around 200 kilometers or 125 miles in diameter, striking at a shallow angle, around 30 degrees or less, and therefore not having penetrated very deeply into the moon. Potential evidence for this theory is suggested by elevated areas northeast of the edge of the South Pole Aitken Basin, possibly representing ejecta from such an oblique impact. Another fascinating aspect of the basin's geology lies in its topography. The basin floor is home to a variety of craters, mountain ranges, and valleys, all shaped by the initial impact and subsequent geological processes. These features make the South Pole Aitken Basin more than just a singularity. It's a complex landscape with a rich geological history. The geological composition of the South Pole Aitken Basin is both complex and diverse. Among its most remarkable features is the diversity of its crust, comprising a variety of lunar rocks and minerals. The great depth of the basin exposes the lunar mantle, offering a rare glimpse of this deep layer of the moon. This exposure is of paramount importance, as it may contain materials uncommon on the surface, providing important clues to the moon's internal structure and composition. The composition of the basin appears to show variations from the usual mountainous regions. Orbital data reveal that the basin floor has slightly higher levels of iron, titanium, and thorium. Mineralogically, the basin floor has a much higher concentration of clinopyroxene and orthopyroxene than the surrounding highlands, which are mainly composed of anorthosite. Several explanations can be put forward for this distinctive chemical signature. On the one hand, it could simply reflect material from the lower crust, which is slightly richer in iron, titanium, and thorium than the upper crust. On the other hand, this composition could be the result of the widespread presence of iron-rich basalt bodies, similar to those constituting lunar seas. The researchers envisage that a large part of the lunar surface surrounding the basin may have been melted during the impact, and the differentiation of this melt layer resulting from the impact could have generated additional geochemical anomalies. Moreover, the likelihood that several processes contributed to the basin's unusual geochemical signature makes the situation more complex. The formation of the South Pole Aitken Basin represents one of the earliest and most significant events in the moon's history. This event not only had an impact on the thermal and chemical evolution of the lunar mantle, but also preserved heterogeneous mantle materials on the lunar surface in the form of ejecta and impact melting. Our journey to explore and decipher the mysteries of the moon is complete. Each mission to its surface, each probe in orbit, and each analysis of its materials brings us a little closer to unlocking its secrets. The moon, a silent witness to Earth's history, holds many mysteries about our planet's past and offers clues to the future of space exploration. However, lunar exploration is not simply an expedition to a space body, but rather a journey back in time to the earliest days of the solar system. The lunar surface is a fascinating and mysterious place, brimming with unique details and features. Every region and every detail has common formation and evolutionary features, but also remarkable individual peculiarities. Each lunar formation has its own name and unique geological history, offering sites of major interest to scientists and astronomers. As space exploration technologies advance, we are lifting the veil on ancient mysteries and accumulating knowledge that could transform our understanding of the universe for generations to come. These discoveries lay the foundations for future space exploration, paving the way for colonization of the moon and beyond, and potentially extending to Mars and other distant worlds.